Hello, and welcome to the next video in my series on basic statistics. And for this video, finite mathematics. The topic in this video is covered in both stats courses and finite math courses. So you may be watching this video in a stats playlist or a finite math playlist, but rest assured it does apply to both. Now just a reminder, these videos are geared towards individuals who are relatively new to stats or to finite math for that matter. So I'll just be covering the very basics. Now this video is a bit different in that I'm covering what is sort of going on under the hood or behind the scenes in stats and finite math. So this is going to be a little bit, I'm not going to say theoretical, but it is trying to show you where things actually come from. Because in my opinion, whether it's in stats or finite math, learning a bunch of formulas and then regurgitating them is not learning. You're just spitting out what someone has fed to you. So this is meant to get over that and have you actually understand where some of these concepts originate. And finally, if you're watching this video because you're having problems in a course, I want you to stay positive and keep your head up. If you're watching this video, it's because you've come pretty far in your education up to this point. So hopefully this video, along with a little bit of hard work, patience, and determination, you can get through it. I have faith in you, and so should you. So let's go ahead and get started. Now this is the next video in our series on basic counting principles, and more specifically, combinations. And again, this is the area where finite math and stats overlap. So the contents of this video you're likely to find in both a stats book and a finite math book, because there are areas where they are exactly the same. So this can inform both. So we're going to talk about one simple example in terms of a problem, but then we're going to go under the hood and see actually where that comes from. So let's go ahead and get started. So here is our example. Okay, now we're not actually going to answer this question specifically in this video, but we're going to set the stage to answer it in a next video. So let's say the value of mortgage loans made by a bank was normally distributed, or were normally distributed, which we mean by bell-shaped. So I'm sure you've heard of this term before or seen it. So a normal distribution is kind of shaped like a bell. So we have a lot of the values in the middle, and then the values taper off as you go to the left and to the right out towards the ends. So the value of the mortgage loans made by a bank or normally distributed are bell-shaped with a mean of $150,000 and a standard deviation of $30,000. So the average or mean mortgage was $150,000, and then the spread from that mean out either direction was a standard deviation of $30,000. Now, let's say you work for the bank, or maybe you're preparing a report for class or whatever it might be, but you have to analyze this information. So the first question you are asked to report is, what is the probability that a randomly selected mortgage was between $90,000 and $190,000? So if you just picked a mortgage at random from the bank's records, what's the probability that it's between $90,000 and $190,000? So in the videos up to this point, you do not have the tools to answer that question, but we are building towards it, and that's the point of this video. Number two, in your report, you wish to include the dollar range of all mortgages in the middle 40%. So the middle 40% would be those mortgages between 30% and 70%. So the average or the mean would be right in the middle of those two. So you can think of the middle as 50% and then 20% in either direction off to the side. And you want to know, what are the endpoints in terms of dollar amount for that range? So you know the mean is $150,000. So what proportion or probability of mortgages are 20% beyond that and 20% below that? And again, we don't have the tools yet, at least in my videos, to answer that question, but we're building towards it. So the first question is the probability of a randomly selected mortgage between a range, And then in number 2, you are given sort of a percentage range and then asked to find the endpoints. So they're kind of mirror images of each other. So let's go ahead and talk about how we get to learning the ways in which we can solve these problems. So let's talk about this idea of curves and normal curves and bell curves. Now, in several prior videos, we discussed counting involving combinations. We asked how many groups or sets of size R can be chosen from a larger group of size N. So we say this as N choose R, and we write it just like that. So an example would be 12 choose 3 is 220. So there are 220 unique sets or groups of 3 that can be chosen from a larger group of 12. And that's just basic combinations. So we know that N is our total group size. So in that case, it was 12. And R is our selection size. In the previous example, it was 3. Therefore, R can be any natural number between 0 and N. We can choose 0, but we cannot choose more than what we had to choose from. So in our previous example, we were choosing from 12. So our R, our selection size, can be anything and including 0 and 12, the natural numbers, which would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that value for R, it has to be some natural number between 0 and N. That's all that statement down there is saying, and that should actually be kind of intuitive for you. So each combination of N choose R has a certain frequency associated with it. So let's take the example of 3 choose R. So 3 is our total, and we're going to choose as selection size R amounts. So we could have 3 choose 0, we could have 3 choose 1, 3 choose 2, or 3 choose 3. So we can't have anything below 0 because that doesn't make any sense. And we can't have like 3 choose 5 because we're only choosing from 3. That doesn't make sense either. So 3 choose 0, 1, 2, or 3. Now if we add up the frequency of each combination, we have the total number of combinations possible for a group size of N and all selection sizes R. And that's a very large word salad, and I know that, so I'm going to show you exactly what I mean by that. So all this means is that 3 choose 0, there's one way of doing that. 3 choose 1, there's 3 ways of doing that. 3 choose 2, there are 3 ways of doing that. And then 3 choose 3, there's one way of doing that. So in the red, that's the frequency of that particular combination out of 3 total things. That's all that means. So if we add all those together, 1 plus 3 plus 3 plus 1 is 8. So when we're choosing from 3 total things, and we choose all the possibilities, so choose 0, choose 1, choose 2, choose 3, there are 8 total combinations that are possible. That's all we mean by that little paragraph there. Now, if we go one step further, if we divide the frequency, which is there in the red, of a certain combination by the total number of combinations, which is there the 8, there in the blue, we have calculated the proportion of all combinations accounted for by that combination. So the frequency is there in the red of each one, and then the total is there in the blue. So for example, 3 choose 2 has the proportion of 3 over 8, or 3/8. Because 3 was its frequency, there are 3 ways to choose 2 things out of 3, so 3 choose 2 is 3. And then the total for groups of 3 is 8. It's just a simple fraction, a simple proportion. So each combination constitutes a part of the whole. So that means all proportions will add up to 1. It looks like this. So 3 choose 0 is 1. So there's one of those out of 8 possible. 3 choose 1 is 3. So there are 3 of those out of 8 possible. 3 choose 2 is also 3. So there are 3 of those out of 8 possible. And then 3 choose 3 is 1 out of 8. So that's 1 out of 8 possible. Now if you add those fractions up, it's 8 over 8, which of course equals 1. So the frequency of each possibility is a proportion of all the total possibilities given that group size. So I've tried to walk you through that very step by step, building upon each thing as we go. But if you need to, go back and listen to it again or pause this slide. And I think if you look at it once or twice, it'll become readily apparent what I mean. Okay, so let's look at this slide I call the terrible twos. Now in this case, we're looking at the larger total group of 2. So on the n column, we have 2. They're all 2 because we're choosing from 2 things. R can be 0, 1, or 2. So our expressions are 2 choose 0, 2 choose 1, or 2 choose 2. Now in the column next to that, under combinations, 2 choose 0 is 1. There is one way to choose 0 things out of 2. Now for 2 choose 1, we have 2. There are 2 ways to choose one thing out of a group of 2. And finally, 1 for 2 choose 2. There is one way to choose 2 things out of 2. Now if you add up all those combinations, there are 4 total possible combinations. So if we want to figure out the proportion, we just do some division. So for 2 choose 0, we have 1 divided by 4, and that equals 0.25. For 2 choose 1, we have 2 divided by 4, that equals 0.5. And then for 2 choose 2, we have 1 divided by 4, which is 0.25. Now if we add up our proportions, 0.25 plus 0.5 plus 0.25, that adds up to 1. So what we can do is we can plot our proportions using a histogram or a vertical bar chart. And it looks like this. So you can see on the left hand side 2 choose 0, remember, was 1 over 4 or 0.25. So that goes up to 0.25 on our graph. 2 choose 1, that had a proportion of 0.5. So that goes up to 0.5 on our graph. And then 2 choose 2 was 1/4 or 0.25, so that goes up to 0.25 on our graph. And of course, the total area there, 0.25 plus 0.5 plus 0.25 equals 1. Now, the height is pretty self-explanatory. Now, in cases like this, we always assume the width of the bar is just 1 unit. It really isn't measuring anything. It's just a unit of 1. So these are actual areas of rectangles. So 2 choose 0 is 1 times 0.25 because its width is 1, its height is 0.25. Same thing for 2 choose 2. Now in the middle, the width of the bar we understand to be 1 times 0.5. So its area is 0.5, just width times height. So when I say area, I want you to understand that the width of these bars is understood just to be one generic unit. So the total area equals 1, and that's the important concept I'm trying to get across in this video. So let's look at our 5s. So I'm not going to go through this whole chart, but I did this chart the exact same way. So we're choosing from a group of 5, so we can have 5 choose 0 all the way up to 5 choose 5. Those combinations are 1, 5, 10, 10, 5, and 1. When you add up all those combinations, it is 32, which is down there in the blue. And in the rightmost column, we just do some simple division. So the total combination of whatever row we're in divided by our total. So 5 choose 0 is 1. 1 divided by 32 is 0.03125. let's say we go down to 5 choose 3. Well, 5 choose 3 is 10. 10 divided by 32 is 0.3125. So it's all we did, the same thing, just simple division using our combinations and then our total. So if we add up all of our proportions over there on the right-hand side, they all add up to 1. So if we graph that, it looks just like this. Same idea. So the area of each bar is the same as its height, because again, we understand the width just to be 1 unit, 1 general unit. So the total area of the bars is 1. Now let's look at tens. This is a very crazy looking chart, and I didn't worry about color coding it or anything because that's not my point. You understand how these numbers come about. So just keep in mind that the combination column is just 10 choose 2 or 10 choose 3, whatever that happens to be. Then we sum all those up at the bottom of the combination column there on the right-hand side. So there are 1,024 different combinations for all the numbers 0 through 10, choosing out of 10. And then all I did was the simple division. So for example, if you look at 10 choose 0, the proportion is 1 divided by 1,024. So that's why it's 0.000977. It's a very small number because we're taking 1 and dividing it by 1,024. And then we can pick another one. Let's say we choose 10 choose 6. There are 210 ways to do 10 choose 6. So 210 divided by 1,024 is 0.205078. And that should make sense because 210 out of 1,024 is about 0.2. Okay, so same idea. Now if we graph this, it looks the same. So the total area of these bars is 1. Now I'm going to do something a little bit different here. Instead of graphing it with bars, I'm going to graph it with a smooth, continuous curve. And it looks like this. Now that shape should look familiar to you. You've probably seen it. Okay, and that's what we're going towards here. Now, if the bars on the left have a total area of 1, what is the area underneath this curve, or this bell shape? Well, the area under that curve is also 1. Now, technically, the graph on the left is the, quote, correct one. Because what we're doing, we are using discrete random variables. So, the graph on the left is technically the correct one for our problem. But I can still graph it using a smooth curve to get across this concept to you. And that is the area in the bars and the area under that curve is 1. It adds up to 1. The difference being one is a discrete bars, the other one is continuous. Now let's look at 20. And again, this is just 20 choose 0 all the way through 20 choose 20. It looks like this. So again, the area of those bars adds up to 1. Now if I graph it with a smooth line, it looks like this. Now that should really look familiar. Okay, that's pretty much a normal curve or a bell curve. And of course the total area under that curve also equals 1. So the area of the bars is 1 and the area under the curve is 1. And let me show you exactly what I mean by that by overlaying these two graphs. So here is the bar version of that graph. So you can see all the bars would add up to 1 if we actually added all of them together. Now look what happens when I overlay the curve. Just like that. So, what do you take away from this picture? This is actually a very important picture to consider when you're studying stats and or finite math. The bar version of our graph, underneath in the orange, is an approximation of the normal curve, or the normal curve-like shape, there in the blue. Okay? So we're looking at the areas underneath each, and the orange is a very close approximation of the area under the blue curve, and that's what we're getting at as we move from one type of data to another. And so what? Okay, so we come to the end and we got to figure out why this is important. So in this example, we were using discrete random variables. So we could only have 10 choose 1, or 10 choose 2, or 10 choose 9. There is no such thing as 10 choose 8.3, or 10 choose 4.7. Okay, that's what we mean by discrete random variables. But as our total group becomes really large, so in this example we went from 2 to 5 to 10 to 20. So as our group became large, our bars became more and more like a curve shape. So that as n became large, as our group became large, our bars looked more and more like a continuous random variable or a continuous curve. So think of this. Think of 1 million choose 0 all the way up through 1 million choose 1 million. We could probably conceivably do that if we had a lot of extra time on our hands and a lot of paper. The numbers would become just goofy long. But we could do it. And we created a bar graph of that. We'd have a graph with 1 million bars across it, smashed into a very small space. Now the thing is, the proportion difference between, say, 1 million choose 567,987 and 1 million choose 567,988, so one apart, the difference between those two is so small as to be practically meaningless. Okay? So the proportion of the total either one of those represents, the difference between them is so small that it's basically zero. It's almost meaningless. And that's because our group size is so large. Unlike, say, 5 choose 1 and 5 choose 3, which are 0.15625 and 0.31250 respectively. Even though those are just a couple numbers apart, their proportion is significantly wider. So the proportion for 5 choose 3 is almost double what it is for 5 choose 1. Now, remember, all the proportion bars in our histogram add up to 1. The total area is 1. As n become large, these discrete examples, the bars, approach a continuous variable, a curve. But they never actually get there. They never actually become a curve. And that's due to the wonderful concept of infinity and calculus. So remember my crazy example of 1 million choose 500,000? Well, think of the number 1 million going all the way up to and towards infinity. It never really actually gets there because you can't really get to infinity. But as we get closer, our bars become curve-like. So the area under that curve equals 1. So, back to our original question. So using the mean and standard deviation of a continuous random variable, along with the fact that we know that area under the normal curve is 1, we can find out all kinds of interesting stuff. So here's our mortgage question again. The value of mortgage loans made by a bank were normally distributed, or bell-shaped, with a mean of $150,000 and a standard deviation of $30,000. So our first question was, what is the probability that a randomly selected mortgage was between $45,000 and $190,000? So think of our curve. Along the bottom, we would place 45,000 on the left, 190,000 on the right. We draw lines straight up in the air, and the area under the curve between those two values is the probability. And that's it. Okay? So, instead of using the discrete combinations, we would actually use the continuous data here in dollars of mortgages. But the probability is just the area under the curve. And we would use $40,000, $45,000 sort of to chop off one end, and then we chop off the other end at 190, and then the area between those is the probability of finding or picking a mortgage between those two number values. Now, find the second part. In your report, you wish to include the dollar range of all mortgages in the middle 50%. So this may be between, I think in the original question I said 40%, but 50% works. In the middle 50%. So that would be the endpoints of the shaded area under the curve that represents a probability or proportion of 0.5. So the area under the curve would be 0.5. Then we go down to the bottom on our axis, and then we would have two dollar amounts, one on the left and one on the right. And that would be the endpoints for our middle 50%. Okay? Now, again, we don't have the tools necessary yet to actually solve this problem. But I wanted to show you where this idea of a normal curve actually comes from. It is sort of a discrete random variable or discrete whatever taken to extremes. So we did 2, 5, 10, and 20, choose whatever. And then we can think of something crazy like 1,000,000. And we did all the million choose whatevers. We'd basically have a solid, not bar chart, but it would be so squished together and the bars so small that it would actually look like a curve. And the probability under that equals 1. And we can chop up and dice up that curve for all kinds of probabilities and endpoints. That's where it comes from. And we'll be doing more of that in the future. Okay, so that wraps up our latest video on combinations. And we started to talk about why the normal curve is what it is. Sort of the way we can derive it, the way we can understand it as a collection of probabilities that are under a curve, and then how we can begin to imagine splitting it up and dicing it up to find both probabilities over a given range and endpoints over a given range. So we may be given two like dollar amounts for mortgages and say, how many mortgages fall? What's the probability a mortgage falls between these two dollar amounts? Or we can say, here's a probability. What are the endpoints? What's the range that represents that probability? And we're going to be doing a lot of examples of that in the future. So again, this is just sort of under the hood stuff. This is where things come from, so you can actually understand what's going on in your class versus just regurgitating a bunch of crap that you've learned but don't really understand why or what it is. Okay, so once again, if you're watching this because you're having a problem in a course, keep your head up, stay positive. I know you can do it with a little bit of hard work, determination, and hopefully this video helps. I have faith in you, and so should you. So thanks for watching, and I look forward to seeing you again next time.